Imagine you are standing in the center of a very, very large field. You can only see so far, can you not? The universe is much like that vast field, but unimaginably bigger. What we call the observable universe is the part of the cosmos from which light has had time to reach us here on Earth. This is since the universe began, about 13.8 billion years ago. It is not the entire universe, mind you. The entire universe could be much larger, perhaps even infinite. Our observable part is like our personal cosmic bubble, our window to the grand cosmic theater. This concept of an observable limit is truly fundamental. It means there's a horizon, a boundary beyond which we simply cannot see, not yet anyway. Think of a ship sailing away from you. At some point it disappears over the horizon. The cosmic horizon is similar, but it is a horizon in time as well as space. The light from objects beyond this horizon has not had enough time to travel the vast cosmic distances to reach our telescopes. So, when we talk about the observable universe, we are talking about a sphere with Earth at its center. Every observer in the universe, if there are others, would have their own observable universe. The significance of this observable universe is immense for us humans. It is everything we can study, everything we can know directly about the cosmos. It contains all the galaxies, stars, planets, and cosmic phenomena that our instruments can detect. It is the ultimate laboratory for understanding the laws of physics under extreme conditions. It tells us the story of cosmic evolution, from the very first moments after the Big Bang to the complex structures we see today. It is a humbling thought that we are a tiny part of this observable expanse, yet we strive to understand it all. So, our cosmic window is not a physical wall or an edge in the traditional sense. It is a boundary defined by the speed of light and the age of the universe. It is constantly expanding, not because the universe itself is necessarily growing into empty space, but because light from ever more distant regions has had time to reach us. Every day, theoretically, our observable universe gets a little bit bigger, by one light day in every direction. This continuous unfolding of the cosmos is what makes its study so very exciting and full of endless possibilities for discovery. So what exactly lies at this edge of our observable universe? It is not a sharp cliff or a cosmic wall as some might imagine. Instead, what we are talking about is the most distant light that has traveled across the cosmos to reach us. This light forms a sort of spherical boundary around us. The edge is the point from which light, traveling since the universe became transparent, is only just now arriving at Earth. This light is incredibly ancient, carrying information from a very young universe. It is the limit of our vision, our cosmic horizon. Beyond this horizon, there is almost certainly more universe. Much more, perhaps, but we cannot see it directly because light from those regions has not had enough time to complete its journey to us. Think of it like this. If you are in a dense fog, you can only see a short distance around you. The fog limits your sight, creating a personal horizon. The cosmic horizon is similar, but it is created by the finite speed of light and the age of the universe. The universe beyond our observable patch is simply too far away for its light to have reached us in 13.8 billion years. The most distant and oldest light we can detect is called the cosmic microwave background, or CMB. This is the faint afterglow of the Big Bang, the very event that started our universe. The CMB comes from a time when the universe was about 380,000 years old. Before this time, the universe was a hot, dense soup of particles and radiation, so opaque that light could not travel freely. When it cooled enough, atoms formed and the universe became transparent. The light released then is what we now see as the CMB, and it effectively marks the boundary of our directly observable universe. Therefore, when we speak of the edge, we are speaking of this surface of last scattering, the point in time and space where the universe transitioned from opaque to transparent. It is not an edge of existence, but an edge of our current observational capability. What happened before the CMB, or what lies beyond the regions from which the CMB originated, are subjects of intense theoretical research. It is a frontier that pushes our understanding of physics to its absolute limits, inspiring us to find new ways to probe these ultimate cosmic mysteries. To talk about the edge of the universe, we need a way to measure truly colossal distances. Kilometers or miles just will not do. The numbers would be too large to comprehend. So, astronomers use a unit called the light year. A light year is not a measure of time, as its name might suggest to some. It is a measure of distance. Specifically, it is the distance that light travels in 1 year through the vacuum of space. Light is the fastest thing in the universe, traveling at about 300,000 kilometers per second. That is incredibly fast indeed. Now imagine light traveling at this tremendous speed for an entire year. The distance it covers is 1 light year. To give you an idea, this is about 9.46 trillion kilometers. Our nearest star system, Alpha Centauri, is about 4.37 light-years away. This means the light we see from Alpha Centauri tonight actually left that star 4.37 years ago. When we look at distant objects, we are therefore looking back in time. The starlight we see is an old photograph telling us how that star looked in the past. This time travel aspect of light years is crucial for understanding the edge of the observable universe. The observable universe is estimated to be about 93 billion light years in diameter. However, since its age is 13.8 billion years, you might wonder how it can be larger than 13.8 billion light years in radius, or 27.6 billion light years in diameter. This is because the universe has been expanding throughout its history. The space itself has been stretching, so an object that emitted light 13.8 billion years ago is now much farther away than 13.8 billion light years. Using light years helps us grasp the sheer scale of the cosmos. When we say a galaxy is 10 billion light years away, we mean its light has taken 10 billion years to reach us. We are seeing that galaxy as it was 10 billion years ago, a much younger version of itself. This allows us to study the universe's history directly. The light from the very edge of the observable universe, the cosmic microwave background, has traveled for almost 13.8 billion years. It is a baby picture of our universe, a truly remarkable cosmic message from the distant past. The cosmic microwave background, or CMB, is truly one of the most profound discoveries in the history of science. It is often described as the afterglow of the Big Bang. Think of it like the residual heat and light from a massive explosion, still echoing through space billions of years later. This faint microwave radiation bathes the entire universe, coming from every direction with almost uniform intensity. It is the oldest light we can detect, a snapshot of the universe when it was merely 380,000 years old. Before this time, the universe was too hot and dense for light to travel freely. The existence of the CMB was predicted in the 1940s by physicists George Gamow, Ralph Alpher, and Robert Herman based on the Big Bang theory. They theorized that if the universe began in a hot, dense state and then expanded and cooled, there should be some leftover radiation. This radiation, they calculated, would have cooled down over billions of years to just a few degrees above absolute zero. It was accidentally discovered in 1964 by Arno Penzias and Robert Wilson, two American radio astronomers who were trying to get rid of some annoying background noise in their radio antenna. That noise turned out to be the CMB. Studying the CMB is like looking at a baby picture of the universe. While it appears remarkably uniform, there are tiny temperature fluctuations or anisotropies within it. These minuscule variations, typically only about 1 part in 100,000, are incredibly important. They represent the seeds of all future structures in the universe. The slightly denser regions eventually, over billions of years, attracted more matter through gravity, growing into the clusters of galaxies and then galaxies, stars and planets that we see today. Without these tiny initial ripples, the universe might have remained a uniform, featureless expanse. The CMB provides compelling evidence for the Big Bang model. Its characteristics, its temperature, its near-perfect black-body spectrum, and its tiny fluctuations all match the predictions of the theory with astonishing precision. Satellites like COBE, WMAP, and Planck have mapped the CMB in increasing detail, giving us invaluable data about the early universe. This includes information about its age, its composition, how much ordinary matter, and dark energy it contains, and its geometry. It truly is a whisper from creation, telling us the story of our cosmic origins. Section 5. Gazing into the deep telescopes as time machines. To explore the far-off galaxies and peer towards the edge of the observable universe, we humans have built extraordinary tools. Our telescopes are not just instruments for seeing farther, they are in essence time machines. Because light takes time to travel, when we look at distant objects we are seeing them as they were in the past. The farther we look into space, the deeper we look back in time. This remarkable property allows us to piece together the history of the cosmos, observing how galaxies formed and evolved over billions of years. Optical telescopes like the Hubble Space Telescope and now the James Webb Space Telescope have been instrumental in this quest. Hubble, launched in 1990, gave us breathtaking views of distant galaxies, some of which were billions of light-years away. It showed us a universe teeming with galaxies of all shapes and sizes. The James Webb Space Telescope, launched in 2021, is designed to see even farther back in time, into the era when the very first stars and galaxies were forming. It observes in infrared light, which is crucial because the light from very distant objects is stretched or redshifted into longer wavelengths by the expansion of the universe. Besides optical and infrared telescopes, radio telescopes also play a vital role. They can detect the faint radio waves emitted by celestial objects, including the cosmic microwave background radiation. Large arrays of radio dishes, like the Very Large Array in New Mexico or the Atacama Large Millimeter Submillimeter Array in Chile, work together through a technique called interferometry. This allows them to achieve the resolving power of a single, much larger telescope, enabling them to see fine details in distant objects that would otherwise be impossible to discern. These powerful instruments, whether on the ground or in space, collect photons, particles of light, that have traveled for billions of years. Each photon carries a piece of information about its source. By analyzing the light, astronomers can determine a galaxy's distance, its chemical composition, the types of stars it contains, and how fast it is moving. This allows us to build a comprehensive picture of the universe's evolution. It is a testament to human ingenuity that we can sit on our small planet and uncover the secrets of such vast and ancient cosmic realms. Section 6. Infant Galaxies, Snapshots from the Universe's Youth. As our powerful telescopes, especially the James Webb Space Telescope, peer closer to the edge of the observable universe, they are essentially looking back to the cosmic dawn. This is the period when the very first stars and galaxies began to form, a few 100 million years after the Big Bang. What we are finding are infant galaxies, looking very different from the majestic spiral and elliptical galaxies we see in the nearby, more mature universe. These early galaxies are often smaller, clumpier, and more irregular in shape. They are undergoing furious bursts of star formation. These snapshots from the universe's youth are crucial for understanding galactic evolution. We can see how galaxies started small, perhaps as collections of gas and dark matter, and then grew over billions of years through mergers with other small galaxies and by accreting gas from their surroundings. The light from these extremely distant objects is heavily redshifted due to the expansion of the universe. This means the ultraviolet and visible light emitted by their young, hot stars has been stretched into infrared wavelengths by the time it reaches us, which is why infrared telescopes like JWST are so essential. Discovering and studying these first-generation galaxies is like finding the earliest chapters of the cosmic story. Scientists are keen to understand when the first stars, known as population 3 stars, ignited. These stars are predicted to have been very massive, composed almost entirely of hydrogen and helium, and to have lived very short, spectacular lives. Their explosions would have seeded the universe with the first heavy elements necessary for the formation of later generations of stars, planets, and indeed life as we know it. Finding direct evidence of these first stars is a major goal. The study of these early galaxies also helps us understand the epoch of reionization. After the universe cooled down and became transparent, when the CMB was released, it was filled with neutral hydrogen gas. However, at some point, this neutral gas was reionized, its electrons were stripped away again by the intense ultraviolet radiation from the first stars and galaxies. Pinpointing when and how this reionization occurred is a key piece of the cosmic puzzle. Observing these infant galaxies provides direct evidence of this transformative period in the universe's history, shaping it into the state we observe today. Section 7. The Unseen Universe, Dark Matter and Dark Energy's Role. When we gaze out towards the cosmic edge, studying the oldest light and most distant galaxies, we encounter a profound mystery. The matter we can see, the stars, gas, and dust that make up galaxies, accounts for only a small fraction of the total mass and energy in the universe. About 27% of the universe's content is thought to be dark matter, and a whopping 68% is dark energy. These are dark because they do not emit, absorb, or reflect light, so we cannot see them directly. Their existence is inferred from their gravitational effects on visible matter and the expansion of the universe. Dark matter's presence was first suspected in the 1930s when astronomers noticed that galaxies and clusters were moving too fast to be held together by their visible mass alone. There had to be some extra, unseen mass providing additional gravity. This invisible matter forms vast halos around galaxies and galaxy clusters, acting as the gravitational scaffolding upon which these structures form and evolve. Without dark matter, galaxies as we know them would likely not have formed, or they would look very different. Its nature remains one of the biggest unsolved problems in physics. We know it's there, but we don't know what it is made of. Dark energy is even more enigmatic and even more dominant. In the late 1990s, observations of distant supernovae revealed something astonishing. The expansion of the universe is not slowing down due to gravity, as was expected. Instead, it is accelerating. Dark energy is the name given to the mysterious force or property of space itself that is causing this accelerated expansion. It seems to act as a sort of anti-gravity, pushing everything apart. Its influence becomes more significant as the universe gets larger. Understanding dark matter and dark energy is crucial for comprehending the ultimate fate and evolution of the universe, including what happens at and beyond our observable edge. If dark energy continues to dominate, the universe will expand faster and faster. Distant galaxies will recede from us at ever-increasing speeds, eventually disappearing beyond our cosmic horizon. This means that, in the far future, observers might see a much emptier universe. The quest to understand these unseen components is a driving force in modern cosmology, pushing us to explore new physics and refine our models of the cosmos. Section 8. New Frontiers, Latest Discoveries at the Cosmic Edge. The quest to explore the universe's edge is a continuous adventure, with new discoveries frequently pushing the boundaries of our knowledge. In recent years, particularly with the advent of the James Webb Space Telescope, we have been treated to some truly remarkable findings. JWST has been identifying galaxies that are even more distant, and therefore older, than previously thought possible. Some of these galaxies appear to have formed surprisingly early in the universe's history, perhaps just 300 to 400 million years after the Big Bang. This challenges some existing models of early galaxy formation. These early galaxies also seem to be more mature or more massive than some theories predicted for such an early epoch. This suggests that the processes of star and galaxy formation might have been more efficient or started earlier than we once believed. Scientists are now busy analyzing the light from these ancient systems to understand their chemical composition, star formation rates, and the presence of supermassive black holes at their centers. It is like finding unexpectedly large trees in what we thought was a very young forest. Another exciting area of research is the search for the very first stars, the so-called population 3 stars. These stars, composed only of primordial hydrogen and helium, are predicted to be extremely massive and luminous, but also very rare and short-lived. Finding direct observational evidence of them is incredibly challenging. However, JWST might be able to detect their signature indirectly, perhaps by observing the chemical enrichment they caused in subsequent generations of stars, or by spotting the supernovae that marked their explosive deaths. This would be a landmark discovery, confirming a key part of our cosmic story. Furthermore, detailed studies of the cosmic microwave background continue to provide insights. While the CMB itself is the edge of our direct view, its subtle patterns tell us about the conditions in the very early universe and can even hint at physics beyond the standard model. Scientists are also looking for signatures of primordial gravitational waves, which could have been generated during cosmic inflation, a hypothesized period of extremely rapid expansion just moments after the Big Bang. Detecting these would open an entirely new window onto the universe's first instance, far beyond the CMB. Section 9. The Endless Journey Implications and Future Quests. The ongoing exploration of the universe's edge with its steady stream of discoveries has profound implications for our understanding of our place in the cosmos. Each new piece of information helps us refine our theories about how the universe began, how it evolved, and what its ultimate fate might be. It underscores the vastness of space and time, reminding us that what we can see is just a fraction of a potentially much larger or even infinite reality. This realization is both humbling and inspiring. It fuels our innate human curiosity to explore and understand. The discoveries about early galaxies, dark matter and dark energy are not just academic exercises, they push the boundaries of fundamental physics. They challenge our current theories and often point towards new, undiscovered laws of nature. For instance, understanding dark energy might require a complete rethinking of gravity or an understanding of the vacuum energy of space itself. The conditions at the edge of the observable universe, so close to the Big Bang, provide a unique laboratory to test these extreme ideas, which we cannot replicate on Earth. Looking ahead, the quest to explore the cosmic frontier will continue with even more powerful instruments and innovative techniques. Future space telescopes, larger ground-based observatories and new types of detectors like those for gravitational waves or neutrinos will open fresh windows onto the universe. We will aim to map the early universe in even greater detail, search for the first stars with more precision, and try to unravel the mysteries of dark matter and dark energy. Perhaps we will even find ways to probe what lies beyond our current observable horizon, if that is even possible. Ultimately, exploring the universe's edge is a journey of self-discovery for humanity. It speaks to our relentless desire to know where we came from and where we are going. The universe is under no obligation to make sense to us, yet we find that through science and reason we can comprehend astonishing aspects of its grandeur. The cosmos invites us to keep looking, keep questioning and keep exploring. And with each step we take towards that distant horizon, we learn a little more about the universe, and in doing so, we learn a little more about ourselves. The journey is truly endless.